Hello everyone, welcome back to another video. So today we are going to take a look at a topic which is very important for problems which involves combinatorics and mathematics. Now this is a pretty basic base topic in for combinatorics. So the topic is binary exponentiation. So we will start with what it is used for. Let's say we are given two integers a and b, and we have to find a raised to power b value of this. Now you may see that you may think that this is pretty simple to find this power. It is very easy to find. So what I can do is I can write a naive approach, which is like multiply a b times. So write a for loop of length b. So the time complexity here would be O of b. So this is naive approach. Now let's say, can we optimize this more? Yes, that is done by using this method of binary exponentiation. What it does is it uses a divide and conquer strategy to find a raised to power b. Now, if you are to find a raised to power b, using binary exponentiation, we can find it in O of log b complexity, where base is 2. How is that? So, let's say if we have to find a raised to power b, then what we can do is we can find a raised to power b by 2 and a raised to power b by 2 and multiply it to get a raised to power b. Now, this is the property of uh, powers. Which property is it? That if let's say I have a raised to power c plus d, this is equal to a raised to power c into a raised to power d. Similarly, if I have to find a raised to power b, I can say that it would be equal to a raised to power b by 2 into a raised to power b by 2. So based on this property, so if we have to find a raised to power b, we go to a raised to power b by 2 and take its square. Then again, if we have to find a raised to power b by 2, we go to a raised to power b by 4, a raised to power b by 4, and keep doing this until we are at a stage where b by 2 raised to power x is 1. That is, a by 2 raised to power x is not 1. Yeah, we can say 1 or we can say 0. Any of them can be a base case. So b by 2x is, let's say, 1. So b by 2x is 1, then b comes out to be 2 raised to power x. This is 2 raised to power x, 2 raised to power x. So x comes out to be log 2 of b. So if we generate a tree, this recursive or uh, this type of tree, it would have depth of length of its depth would be log 2b. So keep dividing b until we reach 1 or 0, where this power becomes 1 or 0. So this is the basic idea of binary exponentiation. strategy is used, divide and conquer, and find a raised to power b. Now there would also be an edge case when b is odd. That is, let's say b is 7. So if we have to find a raised to power 7, we would find a raised to power 3, a raised to power 3, and additional a would be required. So this is the case when the b is odd. If it is even, then we don't need to worry about it. A raised to power 4, a raised to power 4. These two satisfies uh, our value of b. Only when b is odd, we need to additionally multiply a. So let's try to write a pseudo code. Obviously, based on this uh, observation, you might understood it is a recursive type of approach. So let's call the function as binary power of a and b. Let's say I'm calling this. Now in binary power of a and b, what could be the base case? Base case would be if b is equal to 0, then my answer is a itself, because a raised to power 0, my answer is 1, because a raised to power 0 is 1. Now other now next after passing the base case, what we need to do is we need to find binary power of a comma b by 2. Note that b by 2 is floor value of it. Means if b is 7, floor value of b by 2, which is 3.5, and its floor would be 3. So just note this is floor value. If you find result of a raised to power b by 2, then based on odd and else odd and even condition of b. So if b is odd, then what we will return? We will return result into a. Else we will return result into result. So what we are doing is, if b mod 2 is 1, that means it is odd. B is odd. That means this case where we need to find a raised to power 7. What we do is we return a raised to power 3 into a raised to power 3 into additional a to handle the case of that additional odd number. Else we'll return if for even case we just return whatever result we found for a raised to power b by 2 into a raised to power b by 2. So this is the pseudo code. Let's let me show you the exact code. So let's if b is equal to 0, that means base case we'll just return 1. Else we will find call binary power a comma b by 2. Now if b mod 2 is equal to 1, then what we will return is this into a. Else we will return this. Looks good. Let's try some cases. Two raised to power 4 is 18. Let's try 81. Let's try the number. Now let's compare this with the naive approach. Naive approach would be just this for loop until we multiply 5 to our answer. Now this for loop will basically iterate 8 times. Now let's check how much time it takes to uh, how many times this function is called in binary power of 5 8. So whenever uh, whenever the naive approach takes a b number of iterations, but the binary power function takes c log 2 of b number of iterations. You can also make it less if we use this. Yeah, so now there are basically we decreased one more iteration. So log 2 of 8 is 3, 3 plus 1 4. So 4 would be the total number of iterations. So naive approach takes p iterations and binary takes log 2 of p, its floor value, plus 1 number of iterations. You can make this one and keep this as a. Anything works, but it would be much efficient than the naive approach which we are using. Now this is a recursive way of doing it. Now I will also show you how can we do this binary power using iterative method. So now what we'll do is we will declare a result variable with one. Now this is the most optimized binary exponential. Now this and this have same time complexity, but this is iterative function, so this is more optimal in because you are not using any implicit stack and no recursive calls are made, just one single function. Now how this works is it it has similar logic as it is, but a little more intuitive. Now let's say we need to find 3 raised to power 7. So its tree would look like something like this: 3 raised to power 3, then 3 raised to power 1, 3 raised to power 1, and additional 3 raised to power 1, same as this, this. So what we do is we basically convert this into a binary number. So 7 in binary would be 4, 2, 1. Now, whenever you divide a number by 2, that means if we divide 7 by 2, it would be 7 by 2 would be 3. That means it would be in binary it would be 0, 1, 1. So whenever you divide a number by 2, number by 2, its binary representation shifts right. So this is a uh, pretty standard operation, right shift in binary bit manipulation. If you are not aware of it, I would recommend to see some binary bit manipulation techniques. Similarly, when you multiply it, there is left shift. Now, when you right shift it, this is the bit which you are uh, basically neglecting. Now, if this bit is 1, that means 7 mod 2 is 1, and the first bit which it represents is nothing but first bit is nothing but the contribution of 2 raised to power 0, which is 1. All other bits contributes a even number. So if we have to check if the number is odd, we just need to check if its rightmost bit is set or not. So if it is set, what we do is we know that this would be contributed in our binary explanation. So this part, what we do is in our result, we will multiply A. Now, whenever we are doing the right shift and moving forward, we also need to make sure that A is becoming A square. Now, why is that? Let's try to see, try to find contribution according to that binary number. So A is 3 here. Now 3 raised to power 7 can be represented as 3 raised to power 1, 3 raised to power 2, 3 raised to power 4, and this is 0, so there would be no contribution, so 1. So this type of representation can be, and this type of number can be represented like this using this binary. So based on this, this is the logic. Now whenever we are moving from this to its left bit, we'll just make its square. So whenever we are moving from first bit to second bit, we are multiplying, taking square of 3 raised to power 2, so 3 raised to power 4. Again going here, it would be 3 raised to power 8, but this bit is set, not set, so it would be, the contribution of this would be 0. So this is the way of we can represent, and based on this, there is this iterative approach. So first of all, if b, while b is greater than 0, so iterating over all the bits, if b and 1 is 0, now this is a bitwise and what it does is it basically checks if the first bit is set or not. So this is 7, and if we take its AND with 1, what 1 represents 0, 0, 0, and just one bit is set. Now if you take AND of it, all the bits before it would be 0, because in AND we need both the bits to be set. Now if the bit of that number is set, it would give 1. If it is not set, it would give 0. And if it is 1, this would be true. If it is not, this would be false. If it is 1, it will take its contribution and multiply it to our result variable. Now doing right shift means basically moving from this bit to this bit, and whenever we are moving, we are just making a equal to its square. So 3 raised to power 1, 3 raised to power 2, 3 raised to power 4, 3 raised to power 8, 3 raised to power 16, like this. Now in most of the questions on lead code or core forces, we will also be given additional condition, that is we need to print power or whatever answer we are getting with its mod as 1e9 plus 7. So you might have seen some this type of questions a lot, where we need to print the final answer with this final answer mod 10 raised to power 9 plus 7. Now why is that? Because power, let's say if you have to find something like 2 raised to power 1000, so this will go beyond 10 raised to power 18, which is the limit for C++ or uh, Java for storing integer values. So what we do is we take its mod, and for mod there are arithmetic modular arithmetic formulas, and here we would just require one. I will just explain it. So if we have to take a raised to power a into b its mod, then we can expand it like this: a mod, take its mod into b mod, and then complete multiplication with mod. So this is the way of, this is the formula for multiplication, and this is enough for our binary exponentiation, because this is only multiplication requires here. There are also additional one, a plus b. So this is same as this, just change multiply with plus. So a mod plus b mod, whole bracket mod. A mod is a little bit different, plus mod and then bracket mod. Now why is that? Because this might go into negative, and adding mod again would make it positive, and then this is just to make a cyclic change towards such that the number becomes positive. Now if you were to add this in our functions, first of all what we'll pass it as this. We can pass it, we can make it global, anything works. So whenever we take, what we do is we take its mod, and instead of returning this completely, so this could be one way of doing it. You can also separate this and keep do this separately, but you can do like this also. Yeah, so this should be enough for this one, for iterative for recursive binary power. Also for iterative one, whenever we are doing multiplication, just do a mod. Don't do the mod when we are right shifting it, because that would remain same, because that is not something which you are multiplying, and the information stored in B is also important. So mod, don't do mod here. So yes, this is the way, this is how the binary exponentiation works. These are two functions, one recursive iterative, use iterative. You can create this function in your template itself and use it whenever you want. So I do it like this. I have this function in my template and I just use it whenever it is required. Now, to show you an example of this question, this is this is one of the example from LeetCode. So what we have to do is, we are given a digit string, which is good if the digit at even indices are even and the digit at odd indices are prime. So for example, 2582 is good because at uh, 2582 is a good number because at even indices the numbers are even, and not at odd indices the numbers are prime. So what we need to do is, given in integer n, we have to return total number of 2-digit strings of length n. Now if you check, we also need to return the answer with modulo 189 plus 7. Now if you check the constraints of on n, n is 10 raised to the power 15. Let's just ignore n raised to the power 15 and try to find logic. So let's just take a string of length 5. Now if you have studied computronics, this would be a very much easy question, I would say. Based on, we just need to fill what options we have. So first of all, we can fill all the digits from 0 to 9. Now to fill even number digit, what options we have? We have 0, 2, 4, 6, 8. And to fill at odd indices, we must have, it should be prime number, so it is 2, 3, 5, 7. So at 0th index, what we can put? We can put 0, 2, 4, 6, 8. At first index, we need to put prime number, so 0, 2, 3, 5, 7. So here again 0, 2, 4, 6, 8, 2, 3, 5, 7, and 0, 2, 4, 6, 8. Now any combination of this number would form a would form a good number. So 0, 2, 0, 2, 0 would be a good number. 0, 2, 0, 2, 2 would be a good number. So what I'm doing is I'm keeping this four numbers constant, changing this. Then we can do, what we do is 0, 2, 0, 2, 4 is also a good number. 0, 2, 0, 2, 6 is also a good number. 8. So these are the good numbers. Now how many of total this can be? This can be total would be equal to 5 into 4 into 5 into 4 into 5, because if we try to generalize this number into a combination of options, At first position, we have 5 options. At second position, we have 4 options. At third position, we have 5 options. Again 4, again 5. So at even indices, we basically have 5 options, 5 even numbers. We can put any of them in at that position. And at odd indices, we have 4 options. So all the prime numbers from 0 to 9. So this is the way to find the number of good numbers. So if we have n as length, what we can do is we can write a for loop from I equal to 0, I less than n, I plus plus, and let's declare answer equal to 1. So whenever I mod 2 is equal to 0, what I will do is I will multiply answer with, let me just write it more better. So if we have n, what we'll do is we will iterate over I equal to 0, I less than n, I plus plus. If I mod 2 is equal to 0, then what I will do is I will multiply answer with 5, because there would be 5 options, and also take mod with the mod. Else what I will do is I will multiply answer with 4, also take mod, and initially answer would be 1. So this is the naive approach. Now problem here is that n has constraints up to 10 raised to the power 15, but so the simple for loop of 10 raised to the power 15 iteration will give you time limit exceeded. But if you make some observations such that if n was 6, 1 2 3 4 5 6, 5 options would be at odd, 4 options would be at even. So what we have is 5 raised to the power 3 into 4 raised to the power 3 for when n is even. So combination of both the numbers is equal. Now when n is 7, let's just take 5. Here would be 5, here would be 5, here would be 5, here 4, 4. So here answer would be 5 raised to the power 3 into 4 raised to the power 2. So additional combination of this. So what we need to do is we need to find binary power of 5 comma n by 2 plus n mod 2. Let's just make it simple for now. 5 comma n by 2 into binary power of 4 comma n by 2, and let's say it is an answer. If n mod 2 is 1, we need to multiply answer with 5 again, so additional 5, and finally we will return answer. So this is the main solution. Now this will take log of n by 2 complexity. This will take log 2 of n by 2 complexity, and n by 2 is of order 10 raised to the power 15, and 10 raised to the power 15's log 2 would be around 45 to 50 iterations. So overall complexity would be log n for this solution. So let's just try to code this solution. I will copy this binary code, binary power iterative code. Five comma n by 2 a mod, then whenever we have a without multiplication, we take its mod. 4 comma n by 2 now, and finally if equal to 1, then answer equal to answer into 5. So this works, and as you can see, has a very good runtime because all the operations here are optimized. Even this b and 1 is better than checking b mod 2 is equal to 1, and b right shift 1 is also better than b by 2. So all the binary operations, bit operations, are better than arithmetic operations. So whenever you can replace an arithmetic operation with a bit operation, you should do it. So this is everything about binary exponentiation. If you want more idea about this, then there is this blog on CP algorithms on binary exponentiation. You can go through this. These two functions are same as what I explained with mod and all these things. And there are also some practice problems. Now this problem was here mentioned here also. So similarly, there are some problems on code safe code forces which you can try to solve. I hope this topic is cleared, and if you like this video, if you understood the topic, please like the video, and thank you for watching.